So today we are going to continue the lecture on explosion. And if you recall, the difference between fire and explosion is that is in the release of the energy. Fire releases energy in a much slower rate as opposed to combustions. Or explosion. So explosion is also a type of combustion, but the release of energy is more rapid. And if we look at explosion, really, explosion itself can be divided into two different kinds of the explosion, and this is also differentiated by the types of energy release. So the two kinds of explosions are deflagration and detonation. So what are the differences between detonation and deflagration? So deflagration is it's a very fast, hot fire. It moves really fast as you heat something, and then it will ignite that material. The material is cold when it is heated, and then it moves really fast and starts to deflagrate. So the reaction will propagate really fast, but the speed is still less than the sonic velocity, meaning it's a subsonic speed. Whereas for a detonation, it is even faster than deflagration. Okay? And not just that, it also creates a shock wave. So deflagration doesn't create a shock wave, but detonation does. And the reaction front will propagate above the sonic velocity. Therefore, it moves at a supersonic speed. So detonation, because of that shock wave, it causes more damage to the surrounding. Okay, so detonation is more destructive than the deflagration because of that pressure. Okay, so let's watch this short video that shows you the difference between deflagration and detonation. For deflagration, when you do deflagration, it does damage the concrete because there's no shock wave or pressure from the process, but detonation does. It creates that pressure. So when a detonation happens, this is when you have the reaction front and the shock front. It moves together in the same speed. So the reaction front moves at a speed that's greater than the speed of sound. So therefore they move together. It drives the shock front immediately in front of it, and then both of these fronts just move at the same speed. So both this pressure, the reaction, and the shock wave moves at the same speed. So that is why when we measure the pressure change to the distance, you will have this abrupt change of pressure to the peak overpressure, and it suddenly just drops down to ambient pressure, and sometimes it can even go to below ambient pressure, and that's when you have that the blast wave and the vacuum that is created. As opposed to deflagration, in deflagration, the reaction front actually moves lesser than the speed of sound. So that is why the pressure front will move because the pressure front moves faster than the speed of sound. So the pressure front will move first, whereas the reaction front moves a bit slower. Okay, so the pressure front moves away from the reaction front at the speed of sound. So that's why when we look at the chart of the pressure difference, the increase of pressure up to the peak overpressure is a bit more gradual as compared to detonation, and then it also afterwards it gradually decreases to ambient pressure. Okay, so you can see the difference is in the change of pressure to overpressure. So if I combine these two charts together, you can see that detonation normally will have a higher overpressure as compared to the a deflagration. For example, this is a vapor cloud deflagration. And as I mentioned just now, as the overpressure from a detonation decrease, it can go below ambient pressure and have a the vacuum created. So in summary, a deflagration is a combustion process that propagates outward at subsonic speed, which is slower than the speed of sound, whereas for a detonation, it moves, so the explosion moves outward at supersonic speed, meaning that the speed is faster than the speed of sound. Now, let's look at what sort of blast damage can happen from overpressure. So any explosions, whether it's detonation or deflagration, will result in a reaction front moving outward from that ignition source, and then it's preceded by the shock wave or the pressure front. So after that combustible material is consumed, that reaction front will stop, it will terminate, but the pressure wave will continue to move outward. So, and then the blast wave is composed of that pressure wave and wind. And then it is that blast wave that causes most of the damage to nearby buildings and structures. So when you have explosion, the blast wave that is created from the explosion will, first of all, it will break windows, and then the pressure from the blast wave can also cause the exterior walls to be blown in or cave in, and the columns also may be damaged. Okay, so the columns of the building. And then after the breakage of the windows and glasses, and then the exterior wall is blown away, then you know that the movement, you have this upward movement of the blast wave. That upward movement will carry the whole building upward. So it will force all the floors to just move outwards like that. And not just that, further blast wave from after the overpressure, that's the under pressure, and then that's a vacuum, right? So the blast wave would move back to the source of the explosion or the ground zero. That will cause the other side of the building, or from the top of the building, is now being pushed downward. So there's a downward pressure on the roof, and then there's also inward pressure from all the other sides of the building, and causes further damage. So you see first breakage of the glass, it breaks all the column, damage of the column, and then it brings it upwards, and after that it's crushed in downwards and towards the inside of the building. So that is the sort of damage that can happen from overpressure. And different magnitude of the overpressure will cause different kinds of damage. At about 1 kilopascal of overpressure, it will cause breakage of glass at nearby windows. Okay. At a higher overpressure, let's say 2.76 kilopascal, you will have a little bit of minor structural damage, for example, damage on the columns, at the walls, and then at higher magnitude, at 4.8 kilopascal, you will have minor damage to the house structure. 13.8 kilopascal, you have partial collapse of walls and roofs and houses, and complete destruction of houses will occur at overpressure of 34 kilopascal and higher. Okay, so how do we estimate overpressure? Experiments with explosives have demonstrated that overpressure can be estimated using the equivalent mass of TNT and the distance from the ground zero point of the explosion, which we call R. Okay. And empirically derived scaling law is ZE equals to R over mass of TNT to the power 1/3. So we need to find this ZE first, okay, in order to get the overpressure, and we follow these equations. So you have the distance and the mass of TNT. So this is the one that that will be given, or a known amount of TNT. Okay. So that ZE is the scale distance to find the scale overpressure. So to find the scale overpressure, we refer to a chart that looks like this. So this is a chart of a scale overpressure PS versus the scale distance ZE. So for example, if you have a value of a ZE, you go and read upwards and go to the side and read what is the value of the overpressure. And once you have the scale overpressure, so this is scale overpressure, not the actual overpressure, then you can calculate the overpressure using this equation. So the scale overpressure is actually the actual overpressure divided by the ambient pressure. So to find the overpressure, you have to multiply the scale overpressure that we get from that chart, okay, multiply it with the atmospheric pressure, with the which is 101 kilopascal. Okay, so that is the scale overpressure. PO is the peak side on overpressure, and PA is ambient pressure. Or you can also use this equation to find the scale peak overpressure, okay, where you can put in the values of the ZE just now, and then you calculate. Okay, if you don't have that chart, if you do not have that chart, you may use this equation. Let's do an example. Let's say that we have 1 kilogram of TNT. So 1 kilogram of TNT. TNT is like a powder. Okay, it's a yellow powder. So you detonate that TNT. Okay, so 1 kilogram of TNT is exploded. So now you have to compute what is the overpressure from that 1 kilogram of TNT at a distance of 30 meters from the explosion. Okay, so you put the TNT, you put that 1 kilogram TNT 30 meters from you, and then you detonate. So now what is the overpressure that you will feel standing 30 meters from that 1 kilogram of TNT? So to do this, we use the equation to calculate the scale distance ZE first. We know that we are, or you are 30 meters from the explosion, that is R, and the amount of TNT that you put over there is 1 kilogram. So 30 meters divided by 1 kilogram to the power of 1/3 is 30 meters per kilogram. And then we refer to this to the chart, or you can calculate also using that the previous equation. Now ZE is 30. If we read up and remember that the scale down here is logarithmic scale, so 30 will be around, if this is 10, this is 20, and this is 30. Okay, this will be 30. And go to the sides. Oops. We'll give you a scale overpressure of, let's see, this is 0.01, 0.02, 0.03, 0.04, 0.05. I think it's 0.055. Okay, this is 0.055. Oopsie. All right, okay. So the scale overpressure is 0.55, and using this equation to find the overpressure, that means you multiply the scale overpressure 0.055 with the atmospheric pressure of 101.3 kilopascal, and you get an overpressure of 5.6 kilopascal or 0.81 psi. So that is the overpressure that you can feel standing 30 meters from 1 kilogram of TNT. It's for 5.6 kilopascal. So let's say that you are in a building, and the building is getting this 5.6 kilopascal overpressure. So what happens to that building? If you remember the previous table that I showed you, the types of damage that can happen to a building at different magnitude of overpressure. Okay, so this is that same table. So if we look here, 5.6 kilopascal would actually cause minor damage to house structure, or even a partial collapse of walls and roofs of houses, because somewhere between minor damage and partial collapse of wall. Okay. So that means that, yeah, you can have a minor damage to house structure. Okay? Everybody okay?
Okay, Doctor.
I'm assuming everybody is okay because you guys are okay.
Yang 0.05 dapat kana dia tu.
Oh, okay. Let me go back. Where did I get the 0.055 before? Okay, let's go back. It's from this chart. So remember we calculated the ZE, which is the scale distance. Once you get the scale distance of 30, you go to this chart and you read up scale distance is in the x-axis 30, and then you read to the side here, you get 0.055. 0.01, 0.02, 0.03, 0.4, 0.5, and this is 0.055. Okay, so that is the PS, scale overpressure. Okay, so what you want to find is this P overpressure. Okay, so we just multiply PS and PA, and you get P overpressure. Okay. All right.
Oh, thank you.
Let's try this. So now instead of 1 kilogram of TNT, let's say we have 8 kilograms of TNT. We put more, and this time let's stand 60 meters from the explosion. Okay, just now was 30 meters, right? Let's stand a bit further now. What is the overpressure at that distance from the 8 kilogram of TNT if it is exploded? So you do the same calculation. Okay, let's try and do this for a while. Take out your pens and pencil and calculators and papers, and let's try to calculate this. Okay, so should I do it together with you? So remember, the equation to use is ZE equals to R over mass of TNT to the power 1/3, and the distance from the TNT is 60 meters. Oopsie. Oops. Sorry about that. 60 meters divided by 8 kilograms. How 1/3? Okay, somebody give
30.
30.
30. Yes.
It's actually the same as the previous one. Okay, and then you go to the chart to find the PS, the scale over pressure, and this is actually the same as the previous example. Your scale over pressure was tadi 0.055, right? At 30, all right. So 0.055, and then to find the overpressure is the scale over pressure times the atmospheric pressure, and you get 5.6 kilopascal. Okay. Everybody okay?
Okay,
Is
Doctor.
this correct? Correct, right? All right. Now let's use the Probit equation to estimate the impact of the explosion. So just now we used that mass of TNT estimation to calculate the overpressure. So now let's use the Probit equation to estimate the impact of an explosion. If you are given the overpressure. So remember, let's recall the Probit equation. The Probit equation is Y equals to K1 plus K2 times natural log of V, and Y is the Probit value or Probit variable, and K1 and K2 would be the constants for the different types of conditions, and V is the causative variable. And if you remember, for fire, the causative variable was the thermal dosage. In the case of explosion, the causative variable is the overpressure. You can use the overpressure as the causative variable. Okay, so the values for K1 and K2 can be obtained from a lot of books that gives the Probit parameters. In this case, if you look here, we're now talking about explosion. So the K1 and the K2 would be this and this. So these will be the values of the K1 and the K2. And the K1 and K2 given here are for death from lung hemorrhage, eardrum ruptures, death from impact, injuries from impact, injuries from flying fragments, structural damage, and glass breakage. Now let's try and do an example. So remember that this time you are given the peak overpressure. Okay, if you are not given the peak overpressure, you can find the peak overpressure if you know the mass of TNT as well as this distance where you're from, right? Okay, so let's say that we calculated the peak overpressure from the previous examples, and we got the peak overpressure is 47,000 Newton per meter squares. So what fraction of structures will be damaged by exposure to this overpressure? And then find out also what fraction of the people, if exposed to this amount of pressure, will die as a result of lung hemorrhage if your lung explodes and bleeds. And what fraction will have your eardrum structured? And then what conclusion can you make from the effect of this much overpressure? So we use the Probit equation, and And we know now that the overpressure 47,000 Newton per meter squared. For structural damage, we go back to that table just now. Structural damage, the K1 is negative 23.8 and K2 is 2.92. So Y equals to negative 23.8 plus 2.92 natural log overpressure. For death from lung hemorrhage, the K1 is minus 77.1, the K2 is 6.91, and you calculate the Probit variable. Eardrum ruptures, let's look here. Eardrum ruptures, according to this table, K1 is negative 15.6 and the K2 is 1.93, and so therefore you calculate the Probit value here in this equation. Now, can somebody give me the answers for these three? Okay, so for structural damage, can somebody give me the value for Y? What's the value for Y here? Structural damage, anybody?
7.61.
Huh?
7.6131.
All right, excellent. So this is 7.61. Death from lung hemorrhage. Somebody help me calculate. And somebody help me calculate for eardrum ruptures. Okay, so death from lung hemorrhage is? Do you get a negative value?
Yeah.
Yeah.
Okay, so what is the value?
Negative
2.763. Negative 2.763.
Okay. And eardrum ruptures?
5.16.
5.16. Okay, so we have these three Probit values. So don't worry about the negative value. Okay. Let's now check out the so what do we do now? We convert the Probit value to percentage, right? Okay. All right, so that's the answer. Okay, so you remember this table? Transformation from percentages to Probit. So, but we do have Probit now, so we translate from Probit to percentage. And so the first one was 7.61. If you look here, 7.61 is somewhere around between this and this, right? 7.61. Yeah. So therefore, the percent affected is 99.6%. For death due to lung hemorrhage is a negative value, since that the smallest value is 2.67 and there are no negative value. That means that nobody will die out of lung hemorrhage. Okay, so 0% will be affected. And eardrum rupture is 5.16. 5.16, where is it? Somewhere around here, right? 5.16 meaning 56. Yeah, somewhere around 56% or 56.5% will be affected from that much of overpressure, 47,000 Newton per meter squared overpressure. Okay. All right. So the conclusion is this blast is not serious enough. Nobody will die from it. No fatalities, but it can cause structural damage. Okay, almost all structures will be damaged because 99.6% is quite high. Almost all of the structures will be damaged, and about more than half of the people will have eardrum ruptures. 56% of people will have eardrum ruptures if they are exposed to that amount of overpressure. Okay, but nobody will die. All right. Okay, let's try this tutorial. Let's say you have a blast that produces a peak overpressure of 58,000 Newton per meter squared now. So this is a larger overpressure than the previous example. Now calculate what fraction of the glass breakage will happen here due to the exposure to this overpressure. So glass breakage, and then how many people, or what is the percentage of people that will die as a result of the lung hemorrhage. So this is like the one that we did before. And what fraction we have eardrum structure, also like the previous example. And then what conclusions can be drawn from this amount of overpressure. Okay, so I will leave you guys to do this for a bit. And you can, so what we have to do now is the first one is glass breakage. Second one is die due to lung hemorrhage, and the next one is eardrum structure. I think you will need this table, right? This table.
Yes, doctor.
So for glass breakage will be this is the K1 and K2 value. Death from lung hemorrhage is that, and then eardrum structures would be this one. All right, so somebody give me the answers for glass breakage, for lung hemorrhage, and for eardrum structure.
For glass breakage, I got 12.5.
Okay, hang on. Oops. So this is y equals to 12.5.
Yes.
Okay, and then lung hemorrhage is y equals to?
I got negative 1.31.
Okay, excellent. And C, y equals to? Anybody, anyone? Did any of you get this value? 5.57?
Yes, 5.57.
Okay. So 12.5, negative 1.31 is, and y is 5.57. And remember, when you get a negative value for the Probit equation, that means this is 0%. Nobody will die from lung hemorrhage. And then for 12.5 and 5.57, so let's go back here. Oops. 12.5, the highest value is 8.09, so that means 100%. of the building will have the glass broken, and then a 5.57 is somewhere here, 5.57. So 71.5%, 71% or 72%, between 71 to 72% will have eardrum structure, which is a higher percentage than the previous one. The previous one was 56 here. All right. So 100% of glass breakage, and this is 71%. 71%. We have eardrum structure. And what can you conclude from this kind of overpressure? It's not as fatal, right?
But strong enough to completely destroy glass.
Yeah.
And
But
eardrum.
But it's a high percentage of the people can have damage to their eardrums. Their eardrums will rupture. That 71% is a very high percentage, and all buildings will have the glass of the building will break